Okay, so we we have seen the idea of performing computation by hand, maybe with the help of some mechanical machine, essentially. But in the first half of the end of the 19th century and first half of 20th century, the vacuum tube appeared. Vacuum tube are essentially lamps with the grid, and so if you just use a lamp, you can with an electric field, you can use them as diodes, so just to have a current going in one direction. If you put a grid in the middle, you can have a triode, which is a valve, which is essentially an amplifier. So this was used, for instance, in radio and all kind of analog devices. But and they can be used also as digital devices if you let them work in saturation. So essentially in two levels, either ground level, so no current passing, or some current passing. And the problem is that each of these things, let's consider this, for instance, no? You can see here a lot of these vacuum tubes. Well, they you need at least two of them to store just one bit of information. Now, so I shall show you a flip-flop, which is the unit of storage. So you can imagine how many vacuum tube you need to have just a hand. So what it can be, I don't know, the handheld calculator of the 70s. And clearly, with all these vacuum tubes, you have a lot of them failing because they are just like lamp. Actually, they quickly discovered that they tend to fail when you switch computer on because of heat shock. When you start heating, you see here the filament. Clearly, you have a shock that can break the filament, and also clearly increasing the temperature, you increase the risk of a failure. So the idea they discovered that you can extend the life of these valves by making them work at low voltage and never turning the computer off, essentially. So this is 37, you see, a computer, which, for instance, this is famous in the history of computer because it is one of the first to use a digital binary arithmetic, which is not just to show you if I'm able to find here. It is not. It was not trivial the idea to use binary computing because, for instance, the ENIAC, which is one of the very big computer that was used also in the Manhattan Project for building the atomic bomb, it used a base 10 representation. Essentially, if you analyze this circuit, which is the element of a storage of a single digit in base 10, I don't know why in the last 2 days Google Meet tends to lose the sharing of the screen. This is essentially the electronic implementation of the Pascal calculator. The Pascal calculator is very simple. You can build it by hand, not very complex. It is made like this. You have a wheel for the unit, a wheel for the second digit, the power of 10. This is for the power 100 and so on. Each time that you turn the unit wheel, you make it make a complete turn. The 10th wheel makes one step. And when each 10 steps of the 10th wheel, the 100th wheel makes one step. So with this, you can easily sum number. For instance, if you had the number 3, 2, 1 with, I don't know, 4, 6, 2, you first add the highest bit by turning it of, say, 4, so 4 position, so 3 becomes a 7. Then you turn this for the number of the 10th that is the second number. So it may carry, for instance, a 1 digit to this one, and so on. And so then you turn this, and this can carry here, and this can carry here, and so on. So this is a very simple mechanical calculator. This is a real one. And one of the first computer was essentially implementing this logic using valves. So they used essentially 10 valves, maybe something more, to store a single digit in base 10. No? So it is like counting like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So switching, no, and then carry on. But clearly, this is a complete waste of valves in this case, because using digital so binary numbers with say 10 things that can store a unit, you can count from 0 to 2 to the power 10, which is 1024. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17. So not so easy to count with fingers, but using the same 10 flip-flops, you can count up to 1000 instead of 10. So it is really a big difference. Okay, but we remember we are at the beginning of the history of computing, and up to now, the idea of computing, except for the Babbage machine, was not clear how or where to store the data and the compute and the program, because in general all the analogic computers are arranged using say wheels and so on, and so they perform always the same calculation, maybe changing the initial data. And but clearly the idea of storing program, for instance, this is a reading card, I don't know, I think from IBM, that used to sort or to divide the cards into groups according to some data they contain. And all the programming essentially is done in this box here by changing wires. So essentially, you say, suppose that you have, say, 3 or 4 holes in these cars, or maybe just one. If it is punched, it is a man, say a record for a man. If it is not punched, maybe it is a record for a woman. No? Then you have to separate, say, the cars that have records for human by the cars that have, or from the cars that have records for men. So the idea here in this box is just take the wire that signals that there is a hole or not, and wire it to the actuator that sends the card from one side on the other. That's all. I have to reshare the screen. I don't know why it is doing like this. Okay. And okay. So, and the idea is that since you maybe in another task you had to divide the cards, I don't know, accounts that have an income larger than some number and so on. So you can store this kind of program in these boxes, the wiring, and instead of rewiring, use another box that had already stored the program. So the idea of storing the program is not new. The new idea is that of storing it essentially in together with the data. And this is essentially the idea of Turing. A Turing machine is a general purpose machine, even though not easy to build, that can essentially implement any algorithm. And the idea is that you have a tape in which you can read and write things. So essentially, this is a paper tape, but you better think to a magnetic tape. And the kind of instruction are like this. It means if the machine is in state 1 and reads the symbol A, then it switches to state 2 and deletes the content of the cell. So this is a kind of program. So the tape in this case is only for storing data. So this is another one. For instance, if the machine is in state 1 and reads B, then switches to 0 and moves to the right. And so with this kind of tapes, of programs, you can manipulate the data. So for instance, you can swap A for B in a string, no, using this program. For instance, if you are in state 0 and you read an A, go to state 1 and write B. If it is in state 0 and reads B, write and pass to state 1 and write 1 A. Okay, so this is for changing A in B and B in A. Then you have to move, and these are the instructions for moving. If you are in state 1 and you read an A, go in state 0 and move. If you are in state 1 and read B, go in state 0 and move. And this is, say, essentially just an instruction for stopping. Since there is no state 2, no rule for state 2, it stops there. So essentially, this is how for a string AAB, we have first reads the A and converts into B, and then moves. Reads A, converts in B, moves. Reads A, converts. Reads B, converts in A, and moves, and then it stops. So this is the idea of a programming the Turing machine. And it can compute, really, there are very long programs since the possibility of the machine are very limited. But you can, say, count the number of A in a given string and divide it by 2. Or so you can examine if you want this. But this had no, essentially, no, there is a very strict separation between the data and the program, and the program has to be stored somewhere. And you can see that the intuition of one of the intuition of von Neumann is to try to store both data and program in the same place. But first of all, we have to solve a big problem in that time, the problem on where to store data, because we have seen that valves are extremely expensive. So having two valves, two triodes for each bit of information means making a very, very large computers that can be used for, say, storing the data needed for making say a sum between two bits. Just assume that you are dealing with 16 digit numbers for each number, or 16 bits number. you have 16 bits for each of the number. Then then you have to use some other bits to store the intermediate results, to the carry, and so on. So you see that you have already some 100 trials just to make one computation, and maybe you can also have a lot of data. But one of the first storage system came from radars. A radar is very simple. No? You send a stream of electromagnetic wave. They bounce from some obstacle, a fly, an airplane, or a tank, or something like this, comes back, and then you use a fluorescent screen just to have this. But the problem with radars is that the electromagnetic waves also bounce on hills and all the static things. So clearly, if you just are interested in airplanes, no problem, because beyond the airplane there is nothing. But if you want to use the radar for seeing, say, ships or tanks, you have to remove the background. And so the idea is to filter the signal in order to show only things that move, and keep all the static pattern, so remove all the static pattern. And just let me see. Now I've loosened my mouse. Where it is? Okay. And so the idea is to memorize something for the time that it takes to make a turn, so about, say, some thousand or some hundreds of a second, and so to have the same signal as before, and only plot something if you have a difference in these two signals. This is called the delay line. So it is something that in which you put an information, and after sometimes this information comes out from the other hand. And you can use several devices, mechanical, devices. One, for instance, is these mercury filled tubes. If you take a tube, say a meter long, and you have a microphone from one side and a speaker on the other side, you emit a pressure wave from one side. It takes, say, 1,000 of second to reach the other side. Then here you have the microphone. You can reconstruct the signal that you sent 1,000 seconds before, and then having it maybe amplified and reinserted back into the tube. And in this way, you can, so clearly don't store just one signal. You send a train of signals in this tube, then you can resend them. So they are stored permanently in this circuit. When they pass from the amplifier phase, you can read them, or you can replace them with another signal. So essentially, having a delay line, you can have, say, a kind of random memory, clearly quite slow, because you have to wait that the signal exit from one side in order to be able to read it. It is like storing things, say, in a disk, in a hard disk. Instead of having the central memory, you can write, and when it turns back, you can read again the same data. So memory, so mercury filled tubes are one, and also I shall show you in the next in a few slides. For instance, the one that probably it is also here in the physics department somewhere, or in the electronic engineer department, are wires. So you just take a very long wire, some meter long wire of iron, Then you have an actuator that makes a turn in the small turn in this wire. So this perturbation travels all the wire, which is generally in spiral, up to the end. To the end, you have a detector, a kind of microphone that takes the signal, re-injects in the beginning, and so on. And so this is a delay line, which is the first kind of memory. You can have, we shall see that you can have other kinds of memory. And so coming back to the ENIAC and back, so you see that the mainframe started with really important investment in tubes, because, for instance, in this 43 ENIAC, you had, say, 1,000, 5,000 cubes, and with, say, a lot of money. And then the next model is about 1,800 tubes. So you can imagine how many of them were to be changed every day. Yeah? I don't understand why it continues to remove the sharing. And so von Neumann, who was at the time working already for the Los Alamos group, was looking for a way of, say, making automatic calculation clearly for the atomic bomb. And essentially, this needed the problems based on partial differential equations, which are quite different from ordinary differential equation, which can be integrated using some mechanical device. And so when he saw this ENIAC at work, decided that it was the solution, and started thinking on how to improve the performances of this computer. So this is the idea of partial derivatives, but I think you are already you already know the subject. Clearly, you don't solve really partial derivatives. You have to discretize partial derivatives and implement some numerical scheme in order to approximate the numerical derivatives. And so this was also this is just to show that in many cases women have been used to maintain these big computers, because it was assumed, first of all, because it was a wartime, so men were implied in the war in the front, and also because it was assumed that women were more careful and more delicate in order to not to to wreck this set. So before going on, you have this is, for instance, a reconstruction of one of the first storage system for 1 bit. It's a flip-flop. Essentially, it works saying that when you send a signal, this goes, say, in saturation at a high level, and this triggers this one to go to the low level. No? So this is a flip. When you send another signal, you have the reverse, and so one goes up and the other goes down. So there is a feed mechanism between these two tubes, so that if this has a current here, then it triggers here to go down, and so on. And clearly, then you can have, say, you can connect this to another place, and so on. In this, you can see here a lot of batteries, because in general you need at least 100 volts for running these tubes. And since the constructor do not want to have also the power part, he used a lot of these batteries just to reach 100 volts. So this is why you see here a lot of batteries. And okay, we have already seen this. And let me go to the other presentation. This one. And so the von Neumann started thinking on how the architecture of a general purpose computer should work, and the idea is so he produced the memory on this, and the idea is to have, say, the standard architecture that is used up to now, which is called the von Neumann architecture. I mean, you have a central processing unit composed essentially by two things: the control unit and the arithmetic logic unit. So this arithmetic logic unit is the one that can perform sum, multiplication, or AND, or of the bits onto numbers. And this is the unit that can say, if there is something in a certain register, then jump in the code from one instruction to the other, and so on. They need a working memory, and the idea is that you have an input device, which generally for the moment are just a card reading device, and output device, which are in general either a printer or a magnetic tape where to store data. Well, clearly, the input device can be also a magnetic tape from which you can read data. And for the memory, they use this extremely complex thing. It continues to switch off the sharing. I don't know why. And so this is a lot of mercury filled tubes. Each of them is a delay line for 1 bit. And so you have a lot of them so that you can have a delay line for several bits. No? And it had a reading time of the order of millisecond, but it could store about probably some 1,000 words. So each line 1,000 bits and something like this. So very slow memory and very large. And the idea is, in order to have the memory in computer, is the following one. You have in some part of the memory the instruction, so the numbers that the logic unit, the control unit has to interpret. So suppose that you decided to make instruction number, say 10, means read from the memory in the specified the next instruction a number and place it in register number A. Then say instruction 11 is read another number from memory and store it into register number B. Then, for instance, instruction, 21 is make the sum of register A and register B and put the result in register C. And finally, instruction number 18 is take what is in register C and store it in the memory. So you can imagine all the translation of these, say, arbitrary instruction into actual, signals to be sent, things to be read, and so on, needs a lot of coding, because at the end you have to use only the standard gates like OR and so on. This is the big problem. One of the things that have been implemented from the beginning is the idea of program counter. I mean, since generally, unless you have some jump, you have to read the first instruction 0, then instruction 1, then instruction 2, then instruction 3. that are stored in memory in some location. Then instead of having the CPU also to increment from, say, after reading this, you have to increment some register called the program counter in order to pass from 0 to 1, then to 1 to 2, 2 to 3. So the idea is to have this increment automatic. So unless you have to jump in some place, you have automatically, I mean, in hardware, the fact that this program counter increases of the right amount. And what is the right amount? It depends if each instruction has the same length, so the increment is fixed. But if the instruction has different length, clearly you have to jump of different amount according to the instruction. And you shall see that this is one of the problem or one of the aspects that have lasted up to almost now. The idea is to have the kind of approach of designing CPU is either each instruction is the same length. This is called the RISC, restriction instruction, I don't remember what, RISC. Otherwise, if you have an instruction of different length, it is generally called the CISC, complex instruction set. So essentially, all just to the Intel chip were all the CISC up to some times ago. Then they emulate the CISC being RISC. So we shall arrive to this problem. But also from the beginning, they had the same problems. And I said that there are other ways, rather funny ways of storing data. For instance, you can use a tube very similar to TV tube or to radar tube, because in this tube you can write have you seen a movie in which you have radars? No, in the radar you see the swipe of the ray, not tracing. Then you have something that appears and lasts for some seconds before fading out. And the idea is that you can use this time in which light stay on the tube as a memory. I mean, you write down your pattern of ones and zero. They stay there for some time. Then you can reread them because essentially when they are written, there is a charge difference between essentially there are electrons that are stored in some metastable state, and then they decade. So instead of decaying emitting light, you try to keep them to keep the phosphor in the excited state, and then you can reread the information and resend it to the electron gun. And so continuously reading and writing this after some, say, second, you have a memory essentially. So you can write here a certain number of pixels here with or not pixels, so 0 and 1s, reread it after a second and refeed the information at the beginning, and having then rewritten again on the screen. And this is another kind of, say, essentially storing things on in some way, in some place. So you can imagine that, okay, this is essentially the same as before. You can imagine that building a computer at the beginning was not so easy. So quickly they arrived to solve the problem. So how many bits should a memory element have? So at the beginning, clearly everything was not was free. So you see that we already have seen that we can at the beginning they could have either the 10 base computer or binary computers as we have now. Also for binary computer, you have to decide, do I use all numbers of the same size, or I use a number of different sizes? Clearly, at the beginning, all numbers were of the same size, but this means that if you have to store 1, 2, 3, it's the same size if you have to store 1 million, 2 million, 30 million, and so on. So clearly, at a certain point, they decided that, no, okay, let's use some unit, which is now a byte, 8-bit, and then you can have either small numbers, 8-bit, from 0 to 156. So medium size number, say 2 bytes, from 0 to 16,000. Large number, 32 bytes, and so on. But also the concept of byte was not standard. Some computer had the bytes of 9 bits, some of them had bytes of 8 bits. And so you can also have, that was for integers. Floating point numbers are another history, which arrived quite later. For instance, von Neumann was against the implementation of floating point numbers in computer, because clearly you can use an integer as a fixed place number. So suppose you have 10 digits. You can decide that there is a comma or a point, a decimal point, at the 5th digit. And so you have digits that have, say, 5 digits for the integer part and 5 digits for the decimal part, for the fractions. And these are fixed point numbers. And von Neumann said, okay, a good mathematician is able to make the conversion of the range of numbers they need for a computation before, so we don't need the floating point numbers, which are things for women, say, essentially. No, not for real men. Real men has to do everything essentially using integers, scaling everything. Okay, and also because the floating point numbers need a lot of, a lot of hardware more. For instance, we shall see that when personal computers appeared in the early 80s, most of them were not able to do floating point number arithmetics in a chip. So they normally had only integer number manipulation, and if one wanted to implement, say, floating point number, it had to use a library code, so extremely slow and extremely heavy. Only when you wanted to use, for instance, a spreadsheet like Excel, you were suggested to buy also the numeric coprocessor, a hardware chip, put it into the computer so that the computer could do floating point numbers in hardware instead of doing it in software. But another thing that was discovered just at the beginning is that in general, you have to perform the same computation on a large set of numbers. Remember that we started with the partial differential equations. Partial differential equations, once they are discretized, mean to apply the same calculation to all numbers in, say, a 2-dimension or 3-dimension space. So a lot of numbers where you have to apply the same computation. And actually, at the beginning, for instance, also for Neumann, at the beginning, considered using a true parallel computer. So instead of using a general purpose computer as we have now, I mean, a single processor that takes a number in memory, shifts it into some register, makes some computation, and restore things in memory. One could also think of having a lot of small processor arranged in a physical way so that each one sends communication to the neighboring one, each of them doing the same computation, and this would be an extremely efficient way to perform a physical computation, not general purpose one, but physical, yes. This is how, for instance, the Ape machine that Parisi, Cabibbo, and others used for performing computation of high energy physics, and a lot of other parallel machines have been developed, say, clearly some 50 years after this one. But in general, the idea is that even though you don't have these things physically arranged in this way, it is much simpler to have all numbers that you have to, over which you have to perform the same computation, arranged in a sequence in memory, so that you start a pipeline. You take the first one, you perform the computation, you store it. The second, the same computation you store. The third, the same computation and you store, and so on. And this is why in many languages, all say originated from C, for instance, actually vectors are actually, or Fortran, they are actually stored in a sequence way in memory. You cannot store a vector everywhere in memory. If you want a real vector, you have to store all data sequentially in memory. So it is done automatically. You don't have to do now. You don't have to do anything. And so the final architecture of a computer is this one, essentially. So because clearly now you have the problem of the CPU has to retrieve something from memory, perform some computation, and store it in memory, or read something from the input and output device, do something, maybe use memory, and then restore in some other device. Clearly, if you think of doing this, you need a lot of wires. So the idea is to have bus. Bus means that each part, each chip, each element of memory can has access to these three buses. Each bus, consider they are, say, a certain number, for instance, 8 wires. So in the CPU, for instance, wants to read memory, what is contained in memory address 3. So it put 3 on the address bus, and the instruction for read, say instruction number 12. So when the element memory sees that there is a read instruction, it checks if this number is the same as its own address number, it puts the content of this memory in the data bus. And so the CPU, after a while, can read from the data bus what was contained in the address, in the memory address 3. Then it does some computation, and maybe it wants to store the result in memory address 5. So it puts the data on the data bus, the address 5 in the address bus, and the instruction, say instruction number 25 here. When memory element 5 reads 25 and its own address in the address bus, it knows that they have to read things from memory bus and store it in its own storage container, and the same from input and output. So essentially, this is how a general computer works. Clearly, then there are a lot of improvement, optimization, and so on. Coming to binary numbers, I think that you are already quite at handy with these numbers. So you can clearly represent decimal numbers, the ones that you use. 37, for instance, in decimal number means 3 times 10 plus 7. But you can use a binary number, which are the same, but in power of 2. So this means 1 times power of 0, so 1, plus 0 times 2, plus 1 times 4, so it is 5, plus 0 times 8, 0 times 16, 1 times 32. And so at the end you have 32 plus 4 plus 1, and so you have 37. So this is essentially the same as 37. And this is the 15. And when you perform a computation, as is the usual rule. But you have to remember that 1 plus 1 gives 0 with a carry of 1. So 1 plus 1, 0, carry 1. 1 plus 1 of the carry, 0 and carry 1. 1 plus 1 plus 1 is 1 with a carry of 1, and so on up to the end. And so at the end, you have this number, which is the sum or the multiplication, in this case, of these two numbers. So you can do everything using binary number. Actually, multiplication is quite easy because you have just to shift, since I order multiplication by 2, you have just to shift this number of a given amount for each digit, which are 1 here. So you see that you can do this multiplication by summing this plus this shifted by 1 plus this shifted by 2 because of this one, plus this shifted by 3 because of this one. So this is the multiplication. And you see that you can do multiplication just doing 4 sums, which is well, it is a standard multiplication, nothing. And you can also have negative numbers. There are a couple of standards. One is, for instance, the complement of 2, in which if you have the most important digit is 0, it is a positive number. If it is 1, it's a negative number. And the negative numbers are done in such a way, the simple sums is like summing a positive number plus a negative number. So, for instance, minus 1 is the number that the sum the two 1 gives 0. So since 1 is, maybe I can write it down. So 1 is this one, say with 4 bits. So which is the number minus, this is 1. Which is the number minus 1, the sum of this plus this unknown is 0? Clearly, here you needed to have a 1. 1 plus 1, 0 with a carry of 1. But here you needed to have a 1, so that the carry of 1 plus 1, 0, and carry 1. Here you put another 1, so that 1 of the carry plus 1 gives 0. Finally, you put the 1 here. And clearly you have a carry of 1, but this is lost because you have just 4 bits. And so this is the representation of minus 1. And you notice that the most important bit here is 0, which is a positive number. Here is 1, and this is a negative number. So this is a way. There are other possibilities. And so you have to invent all of kind of things. And clearly, binary numbers are quite handy, but you have to use a lot of digits. So decimal numbers are not so easy to be converted into binary number. The solution is to use octal, so base 8, or hexadecimal, so base 16 numbers, because they can be converted digit by digit. So, for instance, if you have the decimal number 8 FD3, This is very simple. This is 3. This is D. This is F. And this is 8. So you see that you can convert directly hexadecimal numbers into binary numbers without, so just having a table, not there is no carry, no things to move from one side to the other. And floating, as I said, the floating point numbers are completely different beasts because there are a lot of also standards here. Hopefully, so luckily, at the end, after many times, we had just one common standard. But for many times, you had the different representations in different computers, so you could not simply copy the bit in one computer having it read in another one, which was a really problem. Suppose that you store the data about an experiment in a magnetic type. They are stored as bit 1 0 0 1 0 0 0 1 0 0 0 1. If they are integer numbers, then you have this standard convention and based to numbers. They are quite simple. But if they are floating point numbers, you have to know how they are stored in memory in order to reconstruct the data. Otherwise, they are just meaningless bits. So the idea is this one. You have a certain, just a bit for the sign. This is not a base 2 complement. Then you have 8 bit, for instance, this is one standard, 8 bit for the exponent, and 23 bits for the mantissa. These are single precision numbers. So the idea is to store a number as the first bit, say, plus or minus. Then you have the mantissa here, which is the decimal part, and then you have 2 to the power given by the exponent. So in the mantissa, you don't have this sign here, this one. So you use the exponent in order to always start with a 1, and so you don't memorize this one. So the leading 1 is discarded, and only the mantissa is kept. Clearly, you see that it is not easy at all, for instance, to make a sum of 2 floating point numbers. Because if you want to sum 2 numbers, you have first to rescale the exponent in order to have the same exponent. Otherwise, you cannot sum the mantissa part. Because you remember, no? If you have, I don't know, 3 to the, just use power 10, 3 to the power 3 plus 4 to the power 4th, this is not so easy to sum. You have to write this, for instance, as 40 to the power of 3. Then you can sum 40 and 3 and becomes 43 to the power 3. So you see that already for doing a sum, you have to be careful. And the same for the multiplication, because you make the multiplication. This is simple for the exponent because you have just to sum the exponent. But 3 by 2, 3 by 4 is 12 times 10 to the power 7. Then you have, okay, in this case it's quite simple, but you have, for instance, to reduce this to the standard exponent, so you have to write it 1.2 to the power 8. So you have to do a lot of manipulation of things in order just to implement a sum over multiplication. And remember that all this has to be done in hardware, not in program. So clearly, you can write a library for manipulating floating point number, which was what was done in the first home computer. But if you wanted to do it fast, you have to do all kind of manipulation by using logic gates, so using wires and transistors and so on. So not easy. And how can be done this? Essentially, you have to start from the work of Boole that was essentially to develop the idea that you can make a correspondence between logic operation and algebraic manipulations using maybe some symbols. For instance, the standard idea is that 1 corresponds to true and 0 to false. Then if you have a statement A and a statement B, A and B can be false or true. Is C false or true? Well, when is C false or true? But the idea is that you can convert A into a number 0, 1, B into a number 0, 1, and then to make the AND or just the multiplication in this case. And this multiplication, I'm very tired of this. This multiplication is, or the minimum, is the result. So you see that you have several ways of converting an logical statement into an arithmetic one, and you can do this for a certain number of elementary function. For instance, the end is also the intersection of the set of all possible say occurrence. I mean, suppose that X is true for a certain number of possibilities. So for instance, is these things red? All red things have this property equal to true. Y is true, for instance, for another set of properties. For instance, is these things flat or spike, or has a spike? And so all red things which are also flat have both of these properties equal to true, and this is given by the intersection of the two sets. And the OR instead is the union of this set. The negation is the complement of the set. And you can also have other operation like the XOR. Another way of representing this operation, which has a direct electronic implementation, is to represent things as a logical gate. In this case, you can assume that the signal is traveling using these wires. So this is the symbol of the AND. So this gives 1 in this wire. 1 can be so high voltage with respect to 0 voltage, if both of them are high or are true. This is an OR, this is a NOT. And the important thing is that you can also implement a relationship in this way, as so for instance implication, equality. So x is x equal to y. For instance, they are equal when they are both 0 or both 1. And you can also manipulate, I don't enter this problem, but you can manipulate Boolean expressions so that, for instance, you can convert a negation of an AND of an OR into an AND, no? And the negation of an AND into an OR of negated things. And so you can manipulate, for instance, there are algorithms that are able to find the minimum number of operation needed to perform a given task. So when you have done this, you can start building more complex things. For instance, this is an XOR. XOR means that it is true if either A is true or B is true, but not both. It is the opposite of equality. Equality is true when they both are equal. XOR is true when they are different one from the other. But you can see that this can be built using two AND, two NOT, and two XOR, and one OR operation. Okay, so this is the equivalence. And so, why do you need this? Because after you have built this in paper, you can take your tubes, your flip-flop, your things, and you can arrange them in order to implement these logic gates. And then with these logic gates, you can build all kind of computation. Clearly, you need a lot of logic gates. I once was I don't remember the name of the village nearby here, where there is an old Olivetti Elea computer that had a lot of cards of this size. Each card was a logic gate with, say, 2, 3, 4 transistors each card, resistor, capacitors, and so on. Each card was a logic gate. It had a rack, a very large rack full of cards, and this was the cabling of the computer. And okay, so just to finish, an important thing is that each Boolean function can be expressed as a table of values because all components can only take two values. So the function can only take two values. So you can make a table of all possible inputs and the corresponding outputs here. And then you can, so this is an arbitrary function, but you can convert this using several rules, either in a combination of and or and not, or for instance in a combination of and XOR. There are several combinations. Why it is important? Because once that you have done your table, for instance, an arbitrary table, I mean, instruction, I don't know, instruction 0 means to send, to raise a signal. So this is one. Instruction 1, so maybe in the command, you mean, suppose when I read instruction 0, I have to put these numbers on the 4 wires of a given bus. When I read instruction 1, I have to put these numbers. When I have instruction 2, I have to put this. So you can write any arbitrary table. Each of these tables can be converted into a set of logic gates. Then you start and you design. Okay, so I need a circuit done in this way in order to, a very large circuit, in order to implement this table. And then you take your circuit, you go to the electronic department, you ask to have them, say, implemented on a card, and this is, say, the logic unit that you need to put into your CPU in order to do the things. And since you can reduce all computation to a small number of elementary gates, you may ask, is there a way of having just one standard gate and use only one things to implement everything? Yes, you can do. You can do either using AND, which is this game, with this gate, or using NOR. So both of them can be used to implement any other gate, and so any function. So at the end, you just need to have a way of constructing in a cheap and fast way an AND gate, and with this you can build a computer. And if you want to do this, and I stop, go to here, to this again, to this site, and just wait a minute. Pronto? Mi posso chiamare tra 5 minuti, sono a fare lezione. Bene. So if you go to this site here, the NAND game, then you can build a whole computer, clearly in a simulated one, using only these mechanical devices, virtual mechanical device, these relays, but clearly you can start with other elements, because essentially the first thing to do with the relay is to build an AND gate, and then with an AND gate you start building the other more complex gate. Then you do this with several bits. You have chips essentially, and then you combine all of them, and with say you build the memory, you build the instruction processor, the control unit, you combine them in the CPU, and then at the end, I haven't shown here, but at the end you arrive simulating a whole computer, clearly a very elementary computer, but with already some thousand of gates, so some 10,000 transistors essentially, or relay, or what you need. Okay, I think that for today is enough, even though so maybe we have some time. If you have questions, there are parts that I skipped too much. Maybe I can show you the NAND game if I'm able to recover the sharing. So let me go to the NAND game. Here is, so if you go here, you have this site, a computer, build a computer from scratch, and so you have a set of tasks. The first is okay, suppose you have two how do you call them, to relay. One which is default on, so it is closed unless you send a signal to this electromagnet that attires, that brings this switch in the off position. So unless you send them a signal here, it is on. Yeah, and the alternative is this one, which is generally off unless there is a signal. And then the first challenge is to build an AND game using the minimum number of these two. I think there is another site with there are all solutions, NAND games solutions. Here it is in GitHub. And so for instance, logic gates, okay, let's see, the NAND, okay, so this is the solution for the NAND game. If you can build an NAND game using just two relay. Then with an AND game, you can build an inverter, which is just an AND game with an AND gate with the two inputs. Then you can build an AND. An AND, you need the two NAND games, so four triggers. And then you can build an OR, you can build XOR, then you can build an half adder. And half adder is something that makes the sum of 2 bits with a carry. Then you can have a full adder, which also takes the 2 bits and the carry that can come from the previous operation and gives the result plus the carry. And so at the end, you can have, they're, I think, the same. Then you can write a multi-header, so something that makes the sum of two numbers. They are 10 here. So no, they are 2. They make the sum of 2 bits with 2 bits with the possibility of having a carry, and then you can have a circuit that makes an increment each time you give a signal. It counts. You can also reset, and then you can build a circuit that are true, that gives a signal if the two numbers are equal to 0, less than 0. So this is essentially the task of building a computer. You have to build all these kind of circuits. This selector is something that takes this input or this input giving this control signal. So essentially it is a demultiplexer of 1 bit. Then you can have a switch, a flip-flop essentially. A latch is a switch without clock, and so you have a register, which is something that stores information. Then you can have, in the end, a RAM, a random access memory. I mean, if you put two bits here and data, you can store or read this data according to a signal and in a given position. Then you can have ALU, so algebraic and logical units that performs, say, a certain number of computation. For instance, this is the code, the arbitrary code of the operation. And so according to the code, they can do either the OR, the XOR, the sum, or something like this, as if I remember well. And then you go on, and you have so you have to essentially you have to implement everything. This is, for instance, opcodes. I mean, arbitrary instructions. You have to implement everything, and so remember that each time you see this, it means what you already get from the previous step. So it is an enormous amount of circuit that are condensed in this symbol. And so finally you have something that is an elementary computer that in the next lesson we shall see how could be used to perform a very, very, very simple operation. So we are still at the beginning of the adventure. Okay, I think that now it is really enough, also because I'm tired of this meet that continues to lose the sharing of the screen. I don't know why. And okay, if you have questions, I'm ready here to answer.
Just a curiosity. The success of the transistor is also depend on the fact of this universal gate, because
no, the universal gates are the same. You can. This is done.
I can make an NAND with just one transistor, no? And
no, you need essentially the same amount. So for
like
I think that for having the elementary NAND, you need these two things here. Each of them, I think, can be done probably with just one transistor, or maybe two. Have to, but I think that a transistor in saturation, it is like essentially one of these relay. Now, because also a valve, also a tube, because if you send in the transistor a signal to the gate, it makes it is open, so the voltage goes to 0. If you don't send it stays up. So essentially, according, if you have common emitter or common base, you have this kind of relay of the other one. So I think that you can assume that these are essentially a relay. Actually, I think that for having something robust, you use two relay here, one driving the other, so that you amplify a lot the signal. You don't have to be concerned with, say, fan out, fan in, but these are technical details. So because the problem is that suppose that the output of a transistor has to be sent to many others. Clearly here you are not concerned, but in practice this has a problem because each of the others absorb a little current. And so if you connect too many of them, even though the transistor is high, they don't have enough signal. So in general, you use two transistors, one for, say, discriminating at the beginning, one for discriminating if it is a higher level, and the other for power up the signal, so that you can then connect a lot of other things without any problem. So I think that, for instance, in the TTL, let me check, but I think that in the classical TTL arrangement, each element is let me see, TTL transistor logic. Here, this is Wikipedia, and the classical, you see, the classical NAND is done by two transistors. Essentially, one is which is discriminates, and the other is for powering up the signal, so that you can connect a lot of other transistors without any problem. So essentially, assume that each NAND is two transistors. So you see
vacuum
that
tube also
all
two
two vacuum tubes essentially are the same.
Okay.
The advantage of transistor is that, first of all, they do not break so quickly as vacuum tubes. They absorb much less, and they work with a voltage of 5 volts instead of 100 volts. And they can be made so small that you can store a lot of them in just some. So at the first, some small packaging, say each transistor of the order of some millimeter. Then in the chips, so you had, I don't know, 15 or 30 transistors in the same package. Then integrated circuit, you had millions of transistors in a small amount of place, but the logic is essentially the same.
Okay, thank you.
And they are faster because they have so small capacity. Because, for instance, if you have something which is in state on and you have to put down, or vice versa, you have a charge inside your system that you have to be neutralized in order to not to remove the space in which the current is forbidden. But this absorbs, it takes some time, and absorbs some amount of current. So the smaller you do things, the faster you can switch on and off. and this is the clock of your system. So with I think that with Tube you can have a clock of the order of tenth of second or maybe hundreds of second, not gigahertz.
Okay.
Okay.
Yep.
Okay. See you next Wednesday. Oh, let me check if it is okay next Wednesday. For the moment, yes, the 21. Okay, the 21st. Okay, see you.
See you. Thank you.
But if you have questions, don't hesitate.
Il discorso è questo, è che